All right, guys, so we're looking at this unit test review with graph theory. First question, very simply, determine the degree of each vertex. What you are going to do is focus on every one of these labeled points. So for example, you're going to focus on point A, and you're going to determine how many paths are coming off of A. There are 2, so I would say that A has a degree of 2. If you go to B, B has a degree of 3. C is 3. D is 3. E is 1, 2, 3, 4, 5, and F is 2. Degree is that simple. Now, what we do with degree is we determine, do we have a circuit, a path, or neither? So first thing we want to do is label degrees. So like this one has a 2, a 3, a 2, a 3, a 4, and a 2. When you have exactly 2 odds, we call that a path. Exactly 2 odds, we call that a path. Let's do the same thing on B. 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, 2, 4, and 4. When everything is even, we call that a circuit. And then let's see what we got. We got a 3, we got a 3, we got a 3, we got a 2, a 3, and a 2. This would be neither. When it doesn't fall under exactly 2 odds or all even, then we would call that neither. Now for the circuit, when we ask for a circuit route, what I'm asking you to do, and on the test it would be labeled already, we're going to say this is A, B, C, D. I'll call that E and F. We need to go around every edge without overlapping an edge. Don't backtrack. That's a circuit route. We can start anywhere we want to. So let's say we start at C for this one. I'm going to go C, B, A, down to E, over to D, back to C. Now we are not done with the circuit. A circuit has to end where it starts, but I must cover every edge. So let's come down to F, over to E, up to B, down to F, over to A, and back to C. I have now made a circuit. So again, covering every edge one time, no backtracking. Because they're all even, I can do that on a circuit. What's the difference between an Euler circuit and an Euler path? Okay, so kind of as I just described to you, a circuit, you can cover or you start and stop at same point. A path, you start and end at different point. And specifically, both of these have no backtracking or no, we'll say no overlapping. Neither of them has overlapping. One you can start and stop at the same point. The other one you'd have to start and end at a different point to get the no overlapping part. Now, for number 3, this is a different scenario. What we have is we have something that turns out is a pathway. Let's see real quick. We have a 2, we have a 4, we have a 3, we have a 4, we have a 3. This is a pathway. The odd numbered vertices are only going to be 2 of them. Well, it doesn't have to only be 2, but pick the 2 odds and then found the shortest route between the odd numbers. Now, so the odd numbers here or the odd vertices are C and E. I have options. I can either do 6 from C to E. I can do C, D, E, which would be 7. That's not shorter. And I can do C, B, E. That's 5. That's the one that I want. Okay, so C and E are my odd numbers. The shortest route is C, B, E, because it's 5. And then we create a copy. Now it looks like I kind of copied it, but what we want you to do is we want you to add literally another copy on it. And now that pathway has become a circuit because everything is even. If you recount, those 3s that we had are now 4s. And it turns out that that 4 at city 2, that B, that 4 is now a 6. And you're going to do the same thing we just did on a circuit a second ago, and you're going to cover everything one time only, but you're going to cover all the new ones as well. Start anywhere you want to. So let's maybe start at A. So if I go A to B, B to C, C to D, maybe I'll go, let's see, let's go B to D, come around on, sorry, D to B, let me say that again, and then B to C, and then come around down C to E. I got to cover everything though, so I'm going to go back to D. Let's see what we got here. Let's come up. Can't go to A yet. So from, oh, where am I? Oh, nope. Yep, nope, 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 nope. Okay, I'm going to start over again, guys. I may have just done a bad pathway. Okay, so we're going to double up that 3. We're going to double up that 2. I got lost in my own numbers for a second. Let's start at D. I'm just going to start somewhere else in hopes that I can keep track of it better. D to C. Let's go C to E. E to D. Let's go D to B. B to A. Nope, back it up. I don't want to do B to A yet. A is going to have to be one of the last ones I do. Let's go B to C. And then C back to B. See, we don't always get these right the first time. Let's go. All right, we'll go B down to E and back up to B. There we are. Head over to A, and from A, head down to D. Now I have it. And if I want the sum, and I'll probably ask you for the sum, you're going to add up all the numbers in this thing. So I'm going to add a 1 plus 3 plus a second 3 plus 2 plus 5 plus 6 plus 2 plus 2 plus 8. Let's see what that is. 9, 14, 20. That's 32. So the most efficient route would be a 32. All right, minimal spanning tree. Now, minimal spanning tree is something different. A minimal spanning tree is the idea that you want to cover every vertex, but not every edge. So I don't need to cover everything on this picture. It may be to your benefit to just kind of redraw your vertices and start connecting. My thought to you is connect with the smallest things you can find first. Just start on small. E to D is a 4. That's definitely the smallest. Let's see. Next smallest I see D to C is a 6. Next smallest I see is A to B is a 7. Let's see. Next smallest I see is a 9. But if I cover that 9, I've created a cycle and I don't need that 9. So I'm going to skip over that 9. I want the 4, I want the 6, I want the 7. Next smallest I see is the 10. And the 10 is good. That is my minimal spanning tree. It turns out I don't need the 12 or the 20. They're too big. I wouldn't use a big number just for the fun of it. So if I want to know my total, of course, let's see, minimal spanning tree happens to be 27. Just add up the numbers on the tree that you drew. All right, create a graph to model each map. Okay, so basically what we're going to do is we're going to create a vertex for each region. And we're going to connect anything that shares an edge. If it just comes to a point together, we don't consider that sharing. If it doesn't touch at all, we wouldn't draw a line. So if I start with 1, 1 touches 2, 1 touches 3, 1 touches 4, and 1 definitely touches 5. Move to 2. 2 touches 1, 2 touches 3, 2 does not touch 4. 2's not at all part of 4. So 2 does not go to 4, 2 does go to 5 for sure. 3 goes to 2, 3 goes to 1, 3 goes to 4, 3 goes to 5. And the only thing that would be left would be 4 and 5, and 5's all the way on the outside, so 4 and 5 is there. Now, if we want to do chromatic number, basically anything that is connected would not be able to be colored the same, like colors. So if we call number 1 blue, 2 cannot be blue, 3 cannot be blue, 4 cannot be blue, and 5 cannot be blue. Move on to another color. Let's say red. If 2 is red, 3 can't be red, but 4 can be red. 2 and 4 are not connected. They are by way of another vertex, but straight line connection, 2 and 4 are not connected. 2 and 5 are connected, can't be the same color. Let's say that we go with purple. Let's see, so purple, 3 can't, 4 we've already colored, 3 and 5 are connected, so can't be, and we'll say black. So black, it looks like the chromatic number is 4. So 2 of those can be the same color. Not each one has to have its own color. All right, same idea down here. So I'm going to very, very quickly do this one. So 1, 2, 3, 4, and 5. All right, 1 hits 2 and 3 and 5, doesn't hit 4. Let's see, 2 hits 1, 2 hits 3, 2 hits 4, and 2 hits 5. 3 hits 1, 3 hits 2, 3 hits 4, and 3 hits 5. 4 hits 3, 4 hits 2, 4 hits 5, and there is ours. So we'll start blue. 2 can't be blue, 3 can't be blue, but 4 can be blue. 5 can't be blue. Move on to the next color, red. Red shares with 3, red shares with 5, okay. Purple, purple 3 shares with 5, and black. So again, chromatic number is 4 on this one. Last question on this review. If you read this, we have, we want to offer a lot of new classes, and we want to not offer certain classes on the same days. So if you read this, each class is represented by a vertex. So I have classes A, B, C, D, and E. And it does tell me if there is a student interested in 2 classes, those 2 vertices are connected by an edge. All right, so Jason is connected with B and E. So B and E are connected. C and E are connected. B and D are connected. B and C are connected. A, D, and E will create a little cycle. A goes to D, A also goes to E, E goes to D. And so there is our graph. So there's the graph that we're going to use, chromatic number. Now, chromatic number, you don't have to physically use colors. I wasn't using numbers on the other ones just because we already had numbers, but you can say this is color number 1. A to B is not connected, so B is color number 1 as well. A is not connected to C, but B is connected to C, so I can't use 1 again. A is connected to D, A is connected to E, can't use 1 anymore, so go to 2. C is 2, C is connected to E, C is not connected to D, so I'm going to call D 2. And then E is connected to all these other ones, so I'm going to call E 3. The chromatic number is 3. So if we want to know if it's the same color, they can be recommended together because the same color means they're not connected. So at time 1, I could do A and B. At time 2, I could do C and D. And at time 3, I could do E. Anything else would lead to connections and overlaps, and that would not be good. All right, hopefully that helps. That is the end of this review. And look for me in another review. There's a second one coming up. Thanks, guys.